This conference will now be recorded.
Hello students, welcome to the PYQ discussions. So today we'll be finishing this 2020 2nd September paper. Then we'll take the last paper on this. Okay, so like I think we have discussed 3rd September, 5th September, and we have remaining 4th September. That also we'll be discussing. Okay, so today we'll be finishing this paper. So let us start our discussions for today. So this figure you can see, this is digital circuit with different gates. So in the following digital circuit, what will be the output Z when the input are 1001, 1101. Okay, so you might be having difficulty to read this. Let me write down in terms of truth table, then it is easy to get the output. Okay, before that let me go with let me just see this output. Let me take output of this. See, these are A, B and Z. So let me take this output to be C, this output to be D, this output to be E. Okay, then this is Z, you know that. Okay, so I'll just write here A input B, then I'll write the outputs also. See, I have 3 outputs, right? 4, 3D, E and then Z. Okay, so this is my truth table. I'll write down the inputs given. See, input 1 0, then 0 0, then 1 1 0 1. Okay, now I have to see what is C, what is D and what is E and Z. So look, this is input A, this is input B. So the output C is actually, it is AND plus NOT, so NAND gate. So this will be, you know, A B whole bar. This will give you A bar plus B bar. Okay, now let me write D. So D you are getting, see, this is A, this is B, so you get A or B. This is OR gate, or output. Okay, now what is E then? E is actually, say, you are getting the input C dot D. Okay, C dot D, C dot D, you're getting C dot D. And what about E? This Z, sorry, what about Z? Z is actually C or E whole bar. Okay, that means C dot E bar, C bar dot E bar. Okay, so you can be up to here also, doesn't matter. So let me get one output here. See, when I have 1 and 0, see what will be C? C will be, see, A bar, 1 bar means 0, or this B bar, that means 0, so this will be 1, output 1. Okay, let me first write the C. See, when, see, at least 1 is 0, then you get output in this. Okay, because A bar B bar, so here also 0 0, that means 1 1, 0 bar 0 bar 1 or 1. 1 or 1 is 1. Okay, then if you have both high or both 1 1, you will get 0 output, and again you will get 1 here. Okay, then go to the D. D is A or B. So A or B means you will get 1 here, 0 here, 1, and then 1 here. Okay, D is simply this A or B. Now E is C dot E, and so you will get E here 1, here 0, here 0, and again you get 1. C dot E, right? Now look, you have this Z, C bar, E bar. Okay, when C and E both 1, you will get here 0. So when one among them is 1, you will get actually 0 output, right? See, I'll just look for, okay, so second input C and E both are actually high, so I'll get output low. So here one is high, another one is low, so you'll get 0 again. So here this is both are low, so you'll get high output here, and then again both are high means you will get low output. So 0 0 1 0. So option C will be the correct answer for this question. Okay, so guys, this is how you can do that. There is another method to do it. Okay, another method to do it, where you will get directly this. Okay, so in terms of, you will get in terms of A or B. Okay, A B. See how we can get. See here, I could write this as A or B, as I was writing A or B. Now see, this is D. So this here, when you write A bar, B bar, and or B, A or B, so you get A bar, B bar, A bar A, that will give you 0, and then you get A bar B plus B bar A and B bar B. So this will be 0, so you will get actually this output will be, output E will be A bar B plus A bar B plus B bar A, like that you will get. Now when you add with this, see A bar plus B bar, so once you take common of this, see, we are just adding A bar B plus A B bar plus A bar plus B bar. This is actually Z. Excuse me. So if I take A bar common, you'll get 1 plus B from there here. Again, if I take B bar common, then you get 1 plus A. So this will be actually 1. 1 plus something means 1 only. So you get A bar here plus B bar. Okay. So A bar plus B bar and whole bar. So this is not Z. Z will be actually, whole bar of this will be Z. So this is, so far it is actually C plus E whole bar. So whole bar will be, see, if I take whole bar, you will get actually A dot B. Okay, now let me see. A dot B means wherever you have, see both are on, there only you will get output. So I will get 0 0 1 0. Okay, so this is using De Morgan's theorem. Also you can do like that. Okay, instead of writing this 4, but this is very easy, you don't have to use any De Morgan's theorem and all. Okay, but you can also write this output as good as this. See, Z is actually simply A dot B. Okay, simply Z dot Z. If you simplify this circuit using De Morgan's theorem, then you get Z is equal to A dot B. If you don't want to do this simplification and all, you have to write this all outputs and then see what are the things. Okay, all right. So I have told you two methods to solve here. One method is using De Morgan's theorem, and the second method I have told you, just write down the truth table, and by doing that you can find out. All right, so let us go to the next problem. Excuse me. So this problem is actually from potentiometer. You can see that a potentiometer wire PQ, this is potentiometer wire PQ, it has length 1 meter. Okay, it has length. See, we can measure the length either this way or this way also, doesn't matter. And this wire is connected to a standard cell. Standard cell means it is the cell, EMF of the cell is known. Another cell E2 of EMF 1.02, that means this one. Okay, E2 is 1.02 volt, is connected with a resistance R and a switch S, as you see in the figure. With switch S open, the null position is obtained at a distance 49 centimeter from the Q. Potential gradient in the potentiometer wire is how much out of this? See, in this case, whatever null point we are getting, you know why we are getting null point at all? What is null point? Null point means there is no deflection in the galvanometer. Okay, if there is no deflection in the galvanometer, that means current flowing through this is 0. Okay, then that means the current flowing through the circuit itself is 0. So when is it possible? Suppose this is my wire. See this J, I'm writing PJ, and see this S is open. That means you have this circuit alone. This circuit alone. So this is the circuit now. So this wire has certain potential drop, right? Okay, potential drop. And see, when I say this is 0 and this is open, I think this is open in the sense, yeah, so current will flow like this. I mean, anyway, so this is switch S is open, so you have closed circuit this. Okay, now you have to tell, so this is internal resistance anyway, so you have to say what is the potential gradient of the wire. Potential gradient of the wire is denoted by K, and that is actually potential divided by length of the wire. That will come as, see, volt per centimeter, it is given in the options. So we have to find out that. See, this length is said, see, from the Q this point where we are getting null point. So with S is open, okay, switch is open, the null position is obtained at a distance 49 centimeter from Q. From Q it is 49 centimeter. This much is 49 centimeter. That means this side is 51 centimeter. So the 51 centimeter wire is actually having the same potential as this, right? So I can write potential gradient into this 51 centimeter, okay, is exactly equal to this much voltage. So in a circuit when there is no current flowing, that means you have to say that this wire also has the same potential as the potential of the cell, okay. So that is why if there is no potential difference, then how do you think that current will flow? So if there is no potential difference in any in like between 2 points in the circuit, then there is no flow of current in that, okay. So here no current flow means there is no potential difference at all. So I can write this equation, right? So what is the value of K? K will be 1.02 by 51 centimeter. This is nearly 0.02 volt per centimeter. Okay, see this point. Okay, so option B will be the correct answer. So you have to actually think that when there is, see, in case of potential, like potentiometer, the wire actually drops certain potential, okay, drops certain potential, okay, drops certain potential, and when you get the null point, that much length of the wire has the same potential as the battery. That is the key point here to solve this problem. Okay, I hope you have understood this. Let me go to the next problem. So this is also an interesting problem. You can see here, this is from collision. So a particle of mass m is moving along x-axis. See, you can see that the speed of the particle is ui, okay, initial velocity of the particle m, okay, and it collides elastically with particle of mass 10m. It is actually colliding, okay. 10m, see, this small m is colliding a particle having mass 10m, which is initially at rest and then moves with half with half its initial kinetic energy. That means this particle itself, the m itself, is moving with its half of its initial kinetic energy, that is final kinetic energy of the particle, okay. So that is what is the information given here. So if sine theta 1 is equal to square root of n sine theta 2, then what is the value of this n? You have to find out that. So this is a collision problem. So whenever there is a collision, so, and this is elastic collision obviously, so you know what you have to do. Elastic collision, there are two things you have to actually, it infers two things. Elastic collision means, so elastic collision infers two things, that one is linear momentum in all dimension, like in all direction, linear momentum will be conserved. See here, linear momentum will be conserved both in vertical direction and horizontal direction, both directions, okay, in all directions I can say. Linear momentum conserved in all directions. And total energy is conserved, at the same time kinetic energy also conserved for perfectly elastic collision, okay. Kinetic energy is conserved and also the total energy is conserved. Okay, total energy also will be conserved. All right, so look, then I can go one by one. Let me first find out what is the velocity of this guy. Okay, if the kinetic energy, so the total kinetic energy, initial kinetic energy is actually half m u1 u square. Okay, then final kinetic energy of this mass will be how much? Half into half m u square. Okay, let us write the final velocity for this small m is, so then half m u1 square, let us say. So this is half m will cancel each other, and u1 will be u by root 2. That means this guy after collision will have a velocity along this direction. It will be, after collision, it will be u1, which is u by root 2. Okay, along this direction, theta 1 direction with respect to the horizontal. Okay, with respect to horizontal. Now what is the velocity of this guy? See, if the half of the kinetic energy is taken by this, then half of the kinetic energy will be taken by the bigger mass. That is obvious, right? So I can write, look, I can write that half into 10m into v square. Initially it was at rest, so final velocity will be half equal to, this will be half m u1 square. Okay, same kinetic energy. Okay, same kinetic energy as this particle, because then it will be total, right? Total, it will be equal to initial kinetic energy, isn't it? So half m I can just strike it out from here also. So v square is equal to see u1 square divided by 10. So u1 is how much? U1 we have got, u1 square will be, see, u square by 2. So this is u square by 2 means, see, u square by 2 like this. Then you know what you get, v is equal to u by root over 20. Okay, so I have got the velocity. See the final velocity for v also. So we have got velocity v for this particle, like 10m particle, is u by root over 20. So these things are done, right? I'll just erase this portions. So now I'll apply. So conservation of kinetic energy I had applied, and I have found out the velocities for both the particles after collision. Okay, so I have got this. Now I have to apply conservation of linear momentum to get the answer here. See, I have two things here. Look, I have two components now. This way, for this u1 has two things, like u1 cos of theta 1 into m. Okay, this is one, and due to this again you will get another one, so that is v cos of theta 2 into m. So this will be equal to, so this is m into u. Okay, right? But see, since initially there was no momentum in the vertical direction, then I can write u by root 2. That means the momentum of this M in the vertical direction sine theta 1 is equal to the momentum of this particle in the vertical direction. They will be equal. They have to cancel each other, so that in the vertical direction there will be no momentum, because initially there was no momentum, linear momentum in the vertical direction. So 10m, here I have to write m, so 10m into u by root 20 into sine theta 2. So this part we don't require according to the question. This one is fine. So mm goes up, this u goes up. Okay, so this will give you root over 10, and this root over 10 will give you this root over 10. So ultimately what you get, sine theta 1 is equal to square root of 10 into sine theta 2. Okay, so here look, this is the thing we have been given, and we have to find out what is the n. So value of n is 10. Okay, so this is the question from the b part. That means you have to get numerical values. Okay, all right, so this is how you have to apply conservation of linear momentum and conservation of kinetic energy to find out this answer. Okay, let us go to the next problem. So this problem says a wire of density 9 into 10 to the power, let us say density is 9 into 10 to the power minus 3 kg per centimeter cube. Kg per centimeter cube. See, centimeter cube, 1 centimeter cube means what in meter? So it will be actually 10 to the power minus 2 whole to the power minus 3. That means, it will be 10 to the power 6. 10 to the power 6 multiplied, then it will be 9 into 10 to the power 3 kg per meter cube. 1000 you have to multiply. Okay, so it was 10 to the power minus 3. Let me check once again. Suppose you have 10 to the power minus 2 meter whole to the power minus 3. Yes, that is fine. All right, so I have got the density in meter cube. So a wire of density 9 into 10 to the power minus 3 kg per centimeter cube is stretched between two clamps 1 meter apart. So the question is this, that there is a wire having density this much, and see this distance is 1 meter. That means the wire has distance 1 meter. It is stretched actually. This is a problem from stretched string. The resulting strain is given. The resulting strain in the string is given. The lowest frequency of the transverse vibration in the wire is dash. Okay, so you have to get the nearest integer value where Young modulus is given. So look, in case of stretched string, we have to find out the lowest frequency. So what is the mode of lowest frequency? This is the mode of lowest frequency, isn't it? This is the mode of lowest frequency. That means this is the half of the wave. So this lambda by 2 is equal to L. So lambda is 2L. Now let me find out the expression for the frequency first. So velocity is actually given by square root of T, that is the tension in the string, divided by mu. Mu is the mass per unit length. Now let me find out what is mass per unit length. See, I can write the total mass to be rho into A into L. A is the area and this is length is the L is the length. So I can find out mu is equal to m by small l, that is rho into a. Okay. So T, see, look, I can write here T is equal to rho a. I'm sorry, mu is equal to rho a. Mu is equal to, I can write rho a. And what about T? T is actually tension. See, in terms of stress, we can write stress is actually um, okay. First, let me write what about mu. Mu, let me write. Okay, mu is actually rho into a. Okay, rho into a. Okay, so we have got the expression for the velocity. Now, what is the expression for the frequency? Frequency will be v by lambda. So v by lambda, that means lambda is 2l. So 1 over 2l t by mu into a. So this t by a is stress, right? T by a is nothing but stress. So stress by mu. So this is the actually expression for the nu. Again, look in this problem, stress is not given directly. What is given? See, I'll just erase this part. Stress is not given, okay? Stress is not given. So what is given is strain and Young modulus. You know, we know that stress by strain is equal to Young modulus, right? Young modulus is stress by strain. Okay? Then I can write stress is equal to Young modulus y into strain. So in place of stress, I can put that value. And finally, what I can write, this frequency expression for the frequency as 1 by 2l square root of, see, Young modulus, I will write Young modulus into strain divided by mu. Okay, mu is mass per unit length. That was, I think, that I had written mu is rho a. Yeah, I see. So it is actually rho a, rho a. From here, it is rho will be there, not mu. Here there will be rho. This will be rho. I'll tell you how. See, we have taken AL rho is equal to m. So mu is equal to m by L is equal to A rho. So A T by A I have written as stress, so it will be rho. All right. So guys, now we have got the expression for the frequency in terms of given parameters rho, then the strain, Young modulus, etc. Now what else you require? Nothing else. You have to just calculate. So look, so I have the expression for final expression. So I'll just erase everything so that I can do the calculation here itself. Look now, here I'll write the final expression and erase this part. So nu is equal to 1 by 2l square root of Young modulus into strain divided by rho. This is the final expression. So let me just erase this so that I can get some space to do the calculation. So 1 by 2l, l is 1 meter, so 2 into 1, that is fine. Now you have got, say, you have got Young modulus to be 9 into 10 to the power 10, and strain you have been given as 4 into, sorry, 4.9 into 10 to the power minus 4 divided by rho we have got like this. Okay, so what we have got, we have got 9 into 10 to the power 3. So 1 over 2. So this portion you can see, if I take this in the so 9 9, I can strike that out. Look, this thing 7, so you will get actually, I think, yeah, so 6, so 3 will be there, so you will get actually here 7 9, sorry, 4 9 0 0. Look how, so this will give you 10 to the power 7 will cancel, so you will have 10 to the power 3 here. Okay, finally 10 to the power 3 will be there if I strike this. Okay, then you will get this much, so you will get 70 by 2, so it is actually 35 hertz. Okay, so this will be answer, 35 hertz. Okay, so this was very simple. If you can come to this expression, okay, y is modulus into strain in by rho. Okay, so hope you have understood this. Let me go to the next problem. Okay, so this problem is very interesting, not very tough, easy only. So let me tell you this first, what the problem is saying. An ideal cell obtain EMF 10. Okay, ideal cell, and this is DC. You can see that is connected in circuit shown in the figure. Each resistance is 2 ohm. The potential difference across the capacitor when it is fully charged. So when it is fully charged, it will not allow further current through this. That means, so there will be no current through this. So the whole current will be passing through this way, one part, another part this way, and these two will meet again, and then it will pass like this. Okay, like this. Okay, so there will be no current through this capacitor and resistance R5 when this capacitor is fully charged. Now see, when this arm is not there, then you look this, see these two are in series with series and parallel to this. So I have, look now, I have equivalent circuit like this. This is my equivalent circuit. So this is R1, this is R2, then this is my R3, and this is R4. So all are actually 2 ohm. So this particular portion is 2 to 4, and this is 2. So I will have equivalent resistance 4 parallel 2, and then in series again 2. So this will 4 parallel, this is actually 8 by 6 plus 2. So you get actually 4 by 3. That means 10 by 3 is the equivalent resistance. Okay, R equivalent. Okay, equivalent resistance is 10 by 3. So what is the total current just coming out from the cell? So current will be, total current will be 10 volt by 10 by 3. So this is in ampere. So this will be actually 3 ampere. Okay, 3 ampere current will be emitting from here, or coming out from the cell. So 3 ampere here. Now this current will be actually branched into 2. So to this it will be 1 ampere, and through this it will be actually 2 ampere. Okay. So now what you get? So again it will be 3 ampere through this. So I have got the current now. You look, what is the potential difference across C, because this C is actually, see, these are these two are actually parallel to this. Okay, see, C is parallel to these two resistor. So this R2 and R4. Okay, this is parallel to this. Okay, since there is no current passing through this, but I have to find out the potential drop or potential across C, right? So potential drop across these two, that means, you know what, so 4 into 10 by, I'm sorry, this current through individual. So yeah, so potential drop across here, it will be 2 volt, and across this is 2 ohm, but current is flowing, so 6 volt across this. Okay, do you understand? So because the current is 2 ohm here through R4, 3 ohm, right? So voltage drop across 3R plus voltage across 2R, like R2. So the total voltage will be 8 volt. Okay, 8 volt. So the answer will be 8 volt. Okay, across the capacitor when the capacitor is fully charged. Now let us take this problem. This is, I think this is the last problem for this session. A light ray enters a solid glass sphere of refractive index mu is given as √3 at an angle 60°. Then the ray is both reflected and refracted at the farther surface of the sphere. The angle in degree between the reflected and refracted rays at the surface. See, if I show you this figure, it will be a little bit uh, clear to you. So this is a solid glass sphere, and my ray is coming in this way. Okay, so it is incident here at P. Now I know this is AR, so refractive index N1 is 1, and the glass has refractive index N2 to be √3. So at this surface at P, I can apply Snell's law. N1 sine 60° is equal to N2 sine R. So this is 1, as I said, and sine 60° will be √3/2, and this is √3 N2 and this sine R. So this will be, sine R will be equal to half, which is, so R is actually 30°. Okay, R is 30°. Now look this figure. Look this figure. So this will be, see, inside there, see, same refractive index all over. So it will actually come an incident at this R angle at this interface. Okay, the further interface at P. So this angle is R. So reflected ray also will be at R. Now I have to find out refracted ray. So this is reflected ray. Reflected ray. Okay. Now reflected ray, and I have to find out now what is I prime, refracted ray. So now I know this √3 at this point. If I apply again Snell's law into sine 30° is equal to sine I prime. In air, refractive index is 1. So from here you look, I get root over 3 by 2 here. This is root over 3, this is half. So sine I prime is equal to root over 3. So this implies I prime to be 60 degree. Okay, 60 degree. So I have got I prime 60 degree, and this, see, this is actually if this is 60 degree, then these two are actually, you can see that this is perpendicular. Okay, this is perpendicular to this tangent. Okay, this is tangent and this is perpendicular, or this is radius actually, you can see that. So this is then 30 degree, this is 60 degree, this is 30 degree. Okay, so this is 30 degree, sorry, let me just, so this is your 30 degree. If this is 30 degree, look, this is perpendicular to this, that means this is actually, this whole thing is 90 degree. Okay, whole thing is 90 degree, right? Now again this is 30 degree, so this will be 60 degree. Okay, so this R and its reflected ray will be perpendicular to the refracted ray. The angle between this reflected ray and refracted ray will be 90 degree. Okay, so this is all for this session today. We'll stop it here. In the next, we'll take the another session of this another shift, I think another date. Okay, we have discussed 5th, we have discussed I think 3rd or 4th. I think 3rd we have discussed, 2nd we have discussed, one more date we will have, 4th September we'll discuss. So next few classes we'll discuss 4th September of this 220 JEE main paper. Okay, PYQ. All right, so thank you for your questions. Bye for today.